Hello and welcome to another Tycho video. Today I would like to talk a little bit about the new Fast Tracker module, which is a new feature in version 12 of the Tycho software. Now FAST is an acronym. It stands for Fast Acquisition of Streaked Targets, and as you might infer from the name, it is designed to detect objects that move quickly across the field of view. In fact, quickly relative to the exposure time, such that they may imprint a trailing or streaked profile. Now, having said that, it is not required that objects have much, if any, streak to them, as long as they have some movement across the field of view. Now, FAST is not a replacement for the synthetic tracker. You would still want to use synthetic tracking if the goal is to detect very faint objects. However, FAST is ideal when you want to detect fast-moving near-Earth asteroids, artificial satellites, or objects that have high variability in brightness. For example, if you dwell in a field and you capture 100 exposures, as long as the object is present on at least 3 of those exposures, then it stands a very good chance at being presented as a solid detection. So I want to spend the rest of this video now to showcase some examples and also to provide some tips and tricks on how you can get the most out of this new detection routine. So with that, let's go ahead and get started. Okay, now before I dive into the detail on these examples, I want to take just a brief moment to share an overview on the current detection algorithms. This will be useful because it will allow us to more easily compare how this new detection algorithm performs. So to that end, I also have some benchmarks I will be sharing, and then we can dive deep into the examples. So to get started with, I have identified 3 different detection algorithms, the first of which is the 4-frame method. Then we have synthetic tracking, and then finally we have algorithms that are tailored specifically towards the detection of streaked objects. So the 4-frame method, which I also refer to as the conventional method, because it has been around for a relatively long amount of time and enjoyed widespread use. It operates by examining 4 images, each spaced 20 minutes apart in time. And most of the professional sky surveys like to use it because it allows them to maximize sky coverage. So the way that works is that they will take a 30-second exposure of a field and then move on to another field of view, take a 30-second exposure of that, and continue to repeat that process, visiting numerous fields of view of the sky until 20 minutes have elapsed, and then they return back to that first field of view and take a second 30-second exposure. And that process itself will repeat until they have accumulated 4 images of a single field of view. Now, while this does allow them to maximize sky coverage, the trade-off is that there is an implicit upper limit on object motion because of the 20-minute gap from one image to the next. So if the object is moving quickly enough, it will simply exit the field of view within that 20-minute duration. So for example, the Pan-STARRS Sky Survey has an upper limit of around 5 degrees per day on streaked objects, which translates to around 15.5 arcseconds per minute. By comparison, objects in the geobelt move at around 900 arcseconds per minute relative to the background stars. Next up, we have synthetic tracking, and the way this operates is by exploring thousands of different trial stacks, each one exploring a different motion vector, and this allows us to detect very faint objects even when their motion is not known in advance. So it allows those with smaller aperture telescopes to compete with the larger aperture telescope. And some statistics here is that since 2020, over 200 near-Earth asteroids have been discovered by amateurs using this technique. And another really interesting statistic is that only 11 Earth-impacting asteroids have ever been discovered while they were still in space. And 2 of those were discovered using the synthetic tracking module of the Tycho software. 2023 CX1 and 2024 BX1. And you can see in the lower left corner here an image of 2024 BX1. Now, just as with any detection method, synthetic tracking does have a couple of trade-offs. One is that the objects must be present in at least 50% of the images. So if you take 100 images, then it must be in that field of view for at least 50 of those images. And that is simply because synthetic tracking in an ideal implementation will compute the median stack. The other trade-off is that processing time does become excessive when the object has fast motion relative to the exposure time. and by extension that of the total dwell time. So what that means is that if you double the dwell time, then the processing time quadruples. Also, if you double the object speed, that also results in a quadrupling of the processing time. So that's synthetic tracking. Next we have algorithms that are tailored specifically towards the detection of streaked objects. And as you might expect, these will generally outperform the other two in this category, but they may not perform very well if the object has short or no streak profile. Now, some of them, such as radon transform, will also perform suboptimally if there are multiple streaks in the same image. So I have a couple of quotes here. The first one is that in applications where multiple streaks are expected in an image, we suggest to apply the same search algorithm iteratively, removing the highest signal noise streak from the input image and then running it again on this subtracted image. So the idea is that the assumption is that if we assume most images do not have more than one or two streaks, then it should not make the search considerably slower. But that is not really an assumption that is valid, especially on a lot of the examples that I will show here in a moment. So with that, those are three different categories of detection algorithms. So now I'm introducing this new detection algorithm. So I've mentioned a few of its advantages already, but just to recap, it allows us to robustly isolate and track multiple objects in the field. So even if you have dozens of streaked objects, it will identify them very efficiently. It also accommodates large variability in object brightness. It can operate on dozens of images at a time, and it will require as few as 2 detections to track and identify an object. It also works well if the object has little or no streak profile, and it is extremely fast at detecting and tracking these objects. So how fast is it? Well, I have a few benchmarks here. The first one here is using CPU computation. I will also show in just a moment how it performs in GPU mode. But this first one, we have a quote here. It says, with our settings running StreakDet on a 4K by 4K image using a single CPU core took approximately 1 minute. So StreakDet is a different detection algorithm. That it's one that is designed to detect strictly streaked objects, as its name might imply. But as you see here, if you were to have 50 images, then the processing time would take 50 minutes. Now, by comparison, F.A.S.T algorithm is able to operate on those same 50 images, the same size images, with a single CPU core in under 1 minute, 0.87 minutes by comparison. So that's a very nice improvement in efficiency. Next we have now a 2023 paper that went into some detail on Euclid DL. So this is an algorithm to identify streaked objects, and it uses GPU hardware to do so. Again, 4K by 4K images, so that's the size of these images. And the Euclid DL, the benchmark there, they used an RTX 3060. In my comparison, I'm using an RTX 2080, which is within 10% of the speed of an RTX 3060. And as you can see here, it took 12 minutes to process 144 images for Euclid DL. By comparison, again with GPU mode, it takes 0.2 minutes to process the same 144 images and the same size images. So this is a huge improvement, again, in processing time. And that is just looking at the detection part of the pipeline. There are other parts to the pipeline as well. So you've detected objects, and you want to track them, and you want to evaluate them. So we have what's called the whole pipeline to do this. And Euclid DL, in that same 2023 paper, said it took 46 minutes to completely process 144 images. By comparison, F.A.S.T algorithm takes under 1/2 minute to process the same number of images. So now you've got a huge, very dramatic improvement in efficiency. So why do we care so much about processing time? Well, for a couple of reasons. One is that we do have, even as amateur astronomers, access to really large sensors. 16, 26, and even 60 megapixel images are not uncommon, and we are able to take a lot of images in a relatively short dwell time. So for example, if you're capturing these fast-moving objects, your exposure time is relatively short. So if you take 90 exposures of a field of view each 10 seconds in exposure time, that's 15-minute total exposure time. And if you were to have some gap between them, say also 10 seconds, then now you've got a 30-minute dwell time. So you would not want to take 46 minutes to process 30 minutes of data. Now, this is being overly generous, in fact, because a lot of the practical examples that I'll be showing here in just a moment actually have even shorter exposure times, typically on the order of 1 second. So if you've taken 90 exposures, 1 second each, that's 1.5 minutes, and typically they'll have oftentimes very little to no gap between them, so that is also the total dwell time, 1.5 minutes. So under that scenario, you especially would not want to have to take 46 minutes or even 30 minutes to evaluate a set of images that were captured in 1.5 minutes. Okay, so this is the first example. Now, just a quick note here before I get started with it, and this also applies to the other examples as well, is that I have already performed the pre-processing steps of calibration, plate solving, and alignment. So just keep that in mind, and if you want to learn a little bit more about those steps, feel free to consult the user guide, which goes into a lot more detail on those steps and more information on how you can perform them. So with that out of the way, again, this is the first example. We have 66 images here. They are each 0.5 seconds in duration, and the total dwell time on the field is 33 seconds. So the goal here is that the processing time should not take any longer than it took to acquire these images in the first place. In other words, it should not take longer than 33 seconds. Now, that may be a bit of a tall order given that these are large images. They are 26 megapixels in dimension, 6,208 by 4,136 pixels in dimension. But in any case, we will find out here shortly how long it takes. So the way to do that is go to Action, Fast Tracker. And when you do that, it will present you with a couple of options here. The first of which is any limits that you may want on the motion and the sensitivity. So the motion limits, if I were using the synthetic tracker, I would apply some sort of motion limit because that does actually make a difference to the processing time. But for the fast tracker, motion limits have no impact to the processing time at all. They are only there to act as a sort of a filter to the generated results. So if you want to apply limits on speed or precision angle, you can do so. But again, it does not have much, if any, impact at all to the processing time. The other option here is the sensitivity. You can choose between standard or maximum. And I almost always choose standard sensitivity, especially if I am doing a sky survey, because I do not want to have a whole lot of false detections. Now, maximum sensitivity is there pretty much only if you're getting really desperate to try to find some really faint object, but even then, the standard sensitivity can find fairly faint detections on its own. So just keep that in mind. You pretty much always want to use standard sensitivity. So with that out of the way, we can click OK, and you can see it is identifying detections, and we give it a moment to do that, and it's already complete. So it already scanned through all 66 images here and identified 3 high confidence detections. And if we want to see what those are, we can go to File, Match with Artificial Satellites, and we give it a moment to do the matching here, and it has completed that operation. And you can see the 3 results here: Meridian 4, a rocket body, and a OneWeb satellite. So if I click on the first result here, you can see what that looks like. And if I double click on it, you can see this animation. So this is a true detection here. The second result here, again, I can double click to animate the frames, and you can see what that looks like. And finally, the third result as well. So that's pretty cool. We could also, if we want to, we could also look at what orbits these satellites have, because these are known satellites. So I could right click on one here, add to TLE propagator, and then choose Attach to Satellite Viewer. So here's what the orbit of that satellite looks like. And I could do the same for the other examples as well. So here we now have the orbits of all 3 detections. So that's pretty cool to see that. So now we are ready to look at the second example. Okay, so this is the second example. So we have 53 images here. They are each 0.5 seconds in duration, and the total dwell time is 26 seconds. As before, these are large images, 26 megapixels in size. So I will go to Action Fast Tracker and use the same settings as before, no limit on motion and standard sensitivity. So I click OK, and we give it a moment here to do the detection. And here are the results returned. We have 2 high confidence, and I can go to File, Match ArtStats to see what, if any, matches we have here. So they both match with a known satellite. The first one is Diapason, and that is a satellite launched in 1966. And the second one is Explorer 40, launched in 1971. So you can see what this first result looks like. So that is a particularly bright satellite detection there. And the second one is really the point of this second example, to show how faint an object can be detected even with standard sensitivity. So as you can see here, if I double click to animate the frames, this is in fact a true detection, and we know that also because it has good agreement with the known satellite. So with that, let's go ahead and proceed to the third example. Okay, so this is the third example, and we have 60 images here. They're each 1 second in duration, and the total dwell time is 1.3 minutes. Now the image size has been reduced by a factor of 4. I operated this in bin 2 mode, so we have 3084 pixels by 2048 pixels in dimension. So that is actually how I typically operate when I am conducting a sky survey, is I will operate with bin 2 mode. And that just, again, helps streamline the operation, makes it a bit faster. But you can run it however you want to. That's just a note on how I did it for this particular example. So here we can go to Action Fast Tracker. And as before, same settings, no limit on motion and standard sensitivity. So we give it a moment, and that was pretty quick. We have 2 objects of reasonable confidence. The first one is high confidence, and the second one is medium confidence. So I can go to File, Match Artificial Satellites, and you'll notice the first one is matched with a known object and the second one is not. So that second one is one that I actually started tracking myself, and I'll do another video on how to do that, how to do initial orbit determination and differential correction. But for now, what I really wanted to show in this example is the ability of the FAST tracker to detect objects that have high variability in brightness. So what that means here is, as I scroll through the frames here, you can see that the object, as it moves here, has a very noticeable change in brightness. So here it is right here, and it starts to become within the noise of the image. So it has now disappeared, and then it starts to re-emerge later. If I scroll some more, you'll start to see here it is on these subsequent images. So that is the variability in brightness that we can see. But nevertheless, the tracker was able to identify it, even though it is present on just a handful of these images. So that is interesting to see this kind of detection. Okay, so this is the fourth example. As you can see, there are 60 images. They are each 30 seconds in duration, and the total dwell time is 37 minutes. The image size is 4264 by 3154 pixels. So with that, let's go ahead and go to Action Fast Tracker, and I will be using the same settings as before, no limit on motion and standard sensitivity. So I click OK and give it a moment here to identify detections. And the purpose behind this example is to show that the FAST tracker can detect not only fast-moving objects that have streak to them, as you can see in this example, as well as in this example here, but also objects that have very little or no streak at all. So with that, if I go to File, Match Asteroids, Comets, you can see that it has identified a number of minor planets in this data set that have very little, or in fact no streak profile to them at all. So for example, if I double click on this result here, you can see This object here, very pinpoint, there's very little, in fact no streak profile on it. And so again, this showcases that the FAST tracker is able to simultaneously detect and track objects that are both very slow moving as well as objects that are very fast moving. So this one here, very fast moving, and on the other hand we have a minor planet that has very little movement throughout this 37 minutes of dwell time. Now if I want to, I can show that more clearly. I can go from the first exposure to the last, and you can see the total movement that has occurred during those 37 minutes. So with that, we can now take a look at the fifth and final example. Okay, so this is the fifth and final example for this tutorial video. As you can see, there are 90 images in this data set. They are each 10 seconds in duration, and the total dwell time is 46.5 minutes. Now, this is certainly on the longer side. I typically advise against having that long of a dwell time if the goal is to detect the fast-moving objects. But in any case, the purpose behind this example is to show that the FAST tracker can detect objects, dozens of them, within the same field of view. So the image size is 3084 by 2048 if you're interested in that statistic. So with that, let's go ahead and go to Action, FAST Tracker. And as before, I will use the same settings, no limit on motion and standard sensitivity. So we give it a moment to identify the objects, and it has completed that. And we go to File, Match Art Sets to see what kind of detections we have here. So these are, for the most part, a lot of geostationary satellites. So if I click on the items here, you can see what they look like in the image viewer. But there are a few that are non-geostationary. For example, one of particular interest is GSAT 6A. This is moving at 1478 arc seconds per minute, and you can see what it looks like here. So if I animate the frames, you can get a better idea of what that detection looks like. So it's pretty cool that it can detect this kind of object. Another interesting bit of information about this object is that it was actually lost for several days shortly after it was launched. And so it's pretty cool that we are able to detect it without too much difficulty with modest amateur equipment. This is, again, with a camera lens at 65 millimeters in aperture. That's about it for this video. I want to thank you for watching and see you next time.